Okay, we are continuing on here with organic chemistry. So we're sort of in the middle and towards the end there of talking about naming alkanes and so forth. So we're going to continue to kind of finish up on that. And I think we may take a detour to chapter 12, talk about alcohols, which I think is in your lab this week. And then we'll come back during discussion and finish the rest of the alkenes and stuff like that. So I think that's sort of the game plan here. But since we're sort of in the middle of talking about obviously naming and stuff like that, let's just kind of finish up that little section of it. And then, like I said, I think we're going to jump to alcohols, and then we'll come back obviously to the other groups here and stuff like that. So we were talking about alkanes, which are really your basis for pretty much all of organic chemistry in terms of naming and stuff like that. The functional group really is sort of the carbon-carbon single bond. They're all single bonded here. As we talked about, it's really, really important to make sure that you do get the first 10 names down for sure, along with the formulas and all that. And that's because pretty much everything is based off of those guys. So everything comes back to those names. So it's really, really important to get those names down. When we do go about naming, it's sometimes referred to as sort of the IUPAC name, and that's the International Union of Pure Applied Chemistry. That's sort of like, if you will, like the formal name, the ones you're supposed to kind of follow all the rules for naming. In organic chemistry, there's a lot of different types of names, like historical names, common names, what Joe calls it down the street type name. But, for the most part, IUPAC naming is sort of the way that most of the time you want to kind of go about naming these guys. To do that, as we talked about, you want to hit the pretty much longest continuous carbon chain. So as we talked about last time, that doesn't necessarily mean it has to be the straightest. You want to basically check all of your options, and again, it could kind of go straight, then go up, and then go over. It could go straight, go down. It could start up at the top and kind of go to the right or left. So you really want to check all your options to try to find the longest continuous carbon chain. The only main rule is you just can't go back over. So you got to go one way until you kind of hit a dead end. And whichever way is the longest, it really should match, in our case, one of those first 10 alkane names. And that means that that's really kind of the base of your name is, be it methane, propane, butane, pentane, whatever those may be. Now, if you do have the option of the sort of the straightest, that's sometimes a good thing to kind of go with, so it makes things easier to see. You can kind of put a box around it, if you will. And then really anything that is not part of that longest continuous carbon chain, anything that's attached, is what is referred to as groups. And a lot of groups, as we'll see here and refresh in just a sec, are sometimes referred to as alkyl groups. And that's sort of a fancy way of saying they're basically carbon groups. And they are, for the most part, also based off of those first 10 alkanes. The difference is they're missing one hydrogen, and they're missing one hydrogen to allow them a chance to bind into the longest carbon chain without having too many bonds. So the nice thing about that is they are pretty much named the same way, except that you drop the last part of the alkane name and you put YL. So instead of CH4, which is methane, we have a CH3 group that is missing one hydrogen. So instead of methane, this is what is known as a methyl group. If you had a 2-carbon group, this is basically based off of ethane. Also, again, missing one hydrogen here to allow it to bond at that carbon on the left there without having too many bonds. And instead of ethane, it is a ethyl group. So you pretty much could roll through the first 10 just like that. It made us missing one hydrogen will be a group. Once you sort of have the longest continuous carbon chain, once you sort of have the groups that are attached, their names, the next thing is really you want to number the longest carbon chain. And in most cases, you'll pretty much have two ways, either like left to right or right to left in most cases. And the goal here with alkanes is you want to number whichever way gives the groups the smaller number. So it is the groups that is the priority here. So you want to number whichever way gives the groups the smallest number. Now, once you do that, and once you choose which way you're going to number, you pretty much have to stick with it in terms of numbering and naming everything. The last thing is really, we then will name the groups that are attached. And it's actually in alphabetical order. And that is regardless of number. So even if you have sort of a big number alphabetically, that is sort of how you put the groups together first in alphabetical order. And also irregardless of a prefix. So again, if you had a couple of methyl groups, you know, a dimethyl, you would still look at the M in terms of alphabetical and not the D for the prefix that is there. Once you have all that, we go basically groups in alphabetical order and then the base of the name. And there's a couple other things that we talked about. If you have a number and a letter, there is a dash between a number and a letter. Also, if you have a letter and a number, letter anywhere, any combination of that, you put a dash between them. If you have two numbers that come in a row, we do a comma between those two numbers. And that's the major way of sort of naming here. Any questions on any of that stuff there? Yeah, let me just kind of, yeah, we're gonna do some in just a second, but we're gonna just draw something down here. Let's see, let's just do all right, I drew something here. Let's see what we did here. All right. So first off, we want to kind of think about the longest carbon chain. So if we were to sort of look at it here, if we went straight across, we would have 1, 2, 3, 4, 5. So that's 5 if we went straight across. If we went straight across and then up, perhaps, that is 1, 2, 3, 4, 5, and 6. So that there obviously is more than 5 from going straight across. The other option would be actually just to kind of go this way. And that would be 1, 2, 3, 4 only if you kind of started at the top there, came down, made a right. So it does look like here, if I am not mistaken, 6 is going to be our longest continuous carbon chain. Again, here you do not see that it is the straightest, which it may not be. So you do want to check all your options there. So we do have 6, I think is what I counted there. 1, 2, 3, 4, 5, 6. So again, sometimes it's helpful just to kind of throw a box around it so we understand that is like the main part of the chain. So 6 carbons would be hexane. Thank you. We also then kind of coming off of these 6 carbons have things that are attached but are not part of the main group. And we got a group right there, which is a 1 carbon group, and that is known as a methyl group. Again, based off of methane, but has the YL. Over here is a chlorine, and that, and they pop up a lot in organic chemistry. And they're named like fluoral, chloral, bromol. We kind of put O at the end of them, iodo. So this would be what is referred to as a chloral group over there. Any questions so far? This is obviously the longest carbon chain. I got my groups going. Now what I'm left with at this point is we want to number. So we could go right to left. And if we did number right to left here, this would be carbon 1, that would be carbon 2, that would be carbon 3, carbon 4, carbon 5, and carbon 6. So we're going in this direction. I have a group at carbon number 3 and carbon number 5 that are basically two located with the right to left numbering. Now, if I numbered it the other way, which would be my other option, which is going obviously left to right, that would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4, carbon 5, and carbon 6. So going left to right, the chlorine is at carbon number 2 and methyl is at carbon number 4. It is as simple as which small? It is the 2, which means we would want to number actually in this direction. It's the smaller number. Any questions on that? So going in sort of the green direction, our chloral groups at carbon number 2, so that would be like a 2-chloral, right? Our methyl groups at 4. And now we basically have all the parts to our names. We have our groups and our numbers, and we have the base of our name. So putting all those guys together, it's going to erase to give me a little bit more room here to write it. Going alphabetical, which means chloral should come first. So regardless of the number, this would be 2. If I had something to write with, it would be 2. Try that again. It would be 2 dash chloral dash 4 methyl. And I'm running out of room, so I'm just going to write it underneath hexane. So, and that's all one word, methyl hexane at the end there. That'll be 2 chloral 4 methyl hexane. Again, methyl hexane, all one word at the end there. And those would be all the steps there. Any questions on that one there? So it really is all about just telling people where everything's located. And it's always the chemistry. Whoever takes the priority, it's always the smallest is sort of the goal of what you want. And you can really just look at the first number versus the smaller number, and that's good enough for the numbering of it. Any questions on any of those steps there? Okay. So let us continue on then, I think. We also talked about isomers, I think. And isomers right at the end there are basically the same molecular formula, but different connectivity. And we kind of tied it together with naming there at the end. And that's a really good way to know whether or not you sort of drew different isomers is if you name them and you get different names, they are different. And if you name them correctly and you get the same name, they are the same, even if they look different. So the deal with isomers, different sort of connectivity in terms of carbons. So again, instead of maybe going 5 in a row, you do 4 in a row and put the other carbon attached somewhere else, or 3 in a row and the other carbons sort of off of those. There is a way to classify carbons. So let's just talk about those real quick here. And we can classify carbons as primary, secondary, and tertiary carbons. And basically, there's a couple of different ways you can think about it, but the simplest way I think personally is you look at the carbon you are interested in, and it's basically how many carbons are attached directly to it. And a primary, since it's 1, it's 1 carbon attached to it. You look at the carbon in a secondary carbon, and it should have directly attached to it 1 and 2 carbons directly attached to it. Actually has 3 carbons directly attached to it. So primary, secondary, and tertiary carbons are ways to classify carbons in organic compounds, and it's based on how many carbons are directly attached to it. Some people tell you to count hydrogens, but you might as well just count carbons. This is an easier way of doing it, I think. So primary, 1 carbon directly attached to whatever carbon you're looking at. Secondary, 2 carbons attached directly to it. And again, tertiary there is 3 carbons directly attached to it. Any questions on that there? Now, we talked a little bit about this a second ago, and there are, again, some different groups that we do see sort of in organic chemistry that are attached to our main chain. And those are alkane substituents. Substituents are just a fancy way of saying basically guys that are attached to the main part of the chain that are not part of the main chain, like our methyl group we saw, our ethyl group, and so forth. As I mentioned earlier, the alkyl groups do have the YL sort of ending at the end of it. And you basically just take the ANE off of the alkane name and drop the YL in it. Halogens, like I said, they kind of end with O, if you will. So these are popular ones: fluoral for obviously fluorine, chloral for chlorine, bromol for bromine, and iodo is for an iodine that is hanging out on there as well. So those halogens really do come up and are alkyl groups. And again, as we talked about, one less hydrogen that allows it to connect without giving carbon, basically too many bonds to it. Here are some alkyl groups and some of the names and where they come from. And there are some historical type names sometimes are used for some groups, but all these are sort of normal ones: methyl, propyl, butyl, pentyl if you had 5, and so forth, hexyl if you had 6. But there is some that are very still used today, and this is one very popular one that pops up a lot. This is isopropyl, and that is a historical name. Whenever you see sort of CH3, CH3 in a row and is part of a group, it's an isopropyl type group. And the difference actually comes from the connectivity of what is being connected or where it's being connected. Now, if we look at basically propane, which is this guy here, basically our 3-carbon guy, which is propane. And to make a propyl group, we're going to take a hydrogen off and allow the connectivity to happen. And there are different carbons in propane. This carbon right here would be a primary, secondary, or tertiary carbon. This carbon is a primary carbon because directly attached to it is just one other carbon, which is the guy in the center. So just one carbon attached. Let's talk about the guy in the center. Guy in the center would be primary, secondary, or tertiary. It would be secondary because he has a carbon to the right and a carbon to the left that is directly attached to it. This would be what is referred to as a secondary carbon. And our carbon at the end here would also be primary, as again, it is attached directly just to the center carbon. That would be a primary carbon, or a 10 if I write it like that. We would make the one bigger. Any questions on the first off, how to identify those? So what happens is sometimes we get groups that, based on where the attachment to the main chain comes from, gives us some different names. This is a propyl group, and sometimes you'll see people call it an N-propyl, N for normal propyl. And basically that accounts from basically removing a hydrogen on a primary carbon. So the attachment comes at the primary carbon there, and that's like your normal propyl group. Could do it the guy on the right, that's the primary carbon, or the guy on the left, which is also the primary carbon, gives you that normal propyl type group. Now, if the attachment or the loss of the hydrogen doesn't come from our primary, but actually comes from our secondary sort of carbon, then we get that propyl group. So if we took off this guy off our secondary carbon, that is where the attachment would go. And if you look to the left, that's CH3, CH in the middle, and CH3, which is our isopropyl group. So by having it attached at the secondary carbon, it's sort of a historical name known as isopropyl. And that's where some of these names sort of come from. You also sort of see isobutyl down there, which has like an isopropyl sort of group attached to it. You got your CH3, CH3 sort of group, but we do have that extra carbon there. So instead of isopropyl, it's known as an isobutyl group, butyl from butane, which has 4 carbons. Also, the attachment here going to happen over here at the primary carbon, but it makes this isopropyl group. You'll sometimes see things like sec-butyl, SEC-butyl, which means it's attaching on the secondary carbon, P-butyl, which means it's attaching on the tertiary carbon to it. So sometimes the alkyl group names sort of come from the attachment which carbon is happening. For us, we will pretty much keep it pretty basic. So it'll be one of the alkanes like methyl, ethyl, propyl. The only kind of weird one I think you'll be responsible for is isopropyl. It does happen a lot, or does pop up a lot. So you should be familiar with isopropyl. Everything else, we won't do isobutyl either, but we'll do isopropyl. But everything else will be probably like a propyl and ethyl type, those type of groups. Any questions on that there? All right. All right, so why don't you take a second here and name this guy and see what you come up with. Longest, I believe. So that is 1, 2, 3, 4. Really, your only other options go straight then down, which would give you 4 as opposed to 5 straight across. So 5 looks like the longest continuous carbon chain. That also means that we got a couple of groups off of it, one there and one there as well. So starting with the base of our name, which is 5, that obviously is all single bonded, so that should be pentane. We got a 1 carbon group, which is based off of methane, which becomes a methyl group. We have our halogen, which is a chloral group. We now have really 2 options to number. We could go left to right, which is 1, 2, 3, 4, and 5. Which gives us groups at carbon 2 and 3. Going the other way, 1, 2, 3, 4, and 5 gives us groups at 3 and 4. So clearly going on the bottom way of numbering there is going to get us the smaller numbers, which is what we want. That means putting this in alphabetical order. Again, we will go with that guy first, which would be at carbon number 2. So that would be 2 chloral dash this guy then would be a carbon number 3. 3, let's see if I can join them up right. Methyl pentane there. So 2 chloral, 3 methyl pentane. Basically the name just telling everybody where you can find things. Pentane saying we got 5 carbons in a row, and at carbon number 2 you should find a chlorine hanging out there. Carbon number 3 should find a methyl group. Yes, sir. There is not, no. So typically you won't do much spacing other than maybe some dashes, and then that would provide some spaces in certain cases, but yeah, no real space between those 2. So let's talk a little bit about cycloalkanes. Remember, cycloalkanes are sort of ring structures. Those are a lot of times just drawn in line structure, as we talked about. Remember, line structure doesn't really put anything on there but lines. Those are things like our triangle, which is our 5-member ring here, which is cyclohexane, and this guy down here, which is cyclohexane. Basically, it's a ring structure, so we put cyclo in front of it. It's all single bonded. And it also has 2 less hydrogens than the straight chain alkane, because again, as those carbons come together, and as we also talked about last time, every time you pretty much make a bond in organic chemistry, you sacrifice 2 hydrogens, 1 on each carbon, and that's what ends up happening here. So if you have what is sometimes referred to as being mono-substituted, meaning that there's just 1 group attached there, you basically just put the name of the group that's there. So our main carbon chain is basically the whole entire thing, which is our cyclohexane. And then the only group that's attached there is our 2 carbon group, and that is our ethyl group there. So that is ethyl cyclohexane. Now you may be asking, do you need to give the number as to where that group is located? And the answer is you do not. Because it is assumed that wherever that group is, that is lucky carbon number 1. So it doesn't really matter. Even if it was drawn to the carbon up on top, that would then be carbon number 1, and it would still be ethyl cyclohexane. You only need to give numbers if there is more than one group attached. So if you had something like this, where we have a methyl group, and we'll just throw down an ethyl group here. In this particular case, we would follow the same procedure. This is our longest carbon chain, which is the ring. It is still 6 carbons, which would be cyclohexane. We have now a methyl group, and we have a ethyl group. So here we do need to give numbers, and we want the smallest numbers. By the way, since the group should go alphabetically, I should start numbering out which one. I should actually start numbering where the ethyl group is, since it needs to go alphabetically first and it's in a ring. That's a good place to start numbering. I then actually should go right to the methyl group, not away from it, right? Because that gives it like a 6 if I kind of go around the other way. So this would be something like 1 ethyl, 2 methyl, and again, cyclohexane runs into it there. So if you have multiple sort of groups attached to a ring, that's when you need to sort of give them. And again, you would probably kind of start maybe with the alphabetical guy. There was a good place to start numbering, but you can do all your options. I could have started with methyl 1 and 2, but again, that wouldn't have went alphabetical. So I went obviously the ethyl 1 and 2. You know, I wouldn't want to start over here and go, this is like carbon 1 and go around. Obviously, that'll give it 2 larger numbers. So we still want the smallest numbers, but obviously here we could get the alphabetical guy, the smallest number out of all of them. Any questions on that? So sure, personally, I think it's sort of the easiest of all of them. And whenever you have a name and you need to draw it, be it the condensed form or the structural form, the line structure, you should always work your way backwards in the name. So you should always start at the end of the name and work your way to the other side. So when I do that, I see heptane, and that means that's basically 7 carbons. And you could simply just lay up 7 carbons, 1, 2, 3, 4, 5, 6, and 7. We'll squeeze them in there. That really takes care of the heptane part of the name. So now we have 1,2-dimethyl and 1-chloral. Those are groups that are attached. So because you are drawing it, you basically could decide which way is 1. So for me, I'm going to decide that this guy right here is carbon number 1. Could have the guy on the other side is carbon number 1. Since you're drawing, it doesn't really matter. And if that is carbon number 1, that means there should be a methyl group hanging off of that. And there's also another methyl group at carbon number 2, which should be right next door, hanging off of that. And that takes care of my dimethyl at the proper locations for it. Now what's left is 1-chloral, which means at carbon number 1, there should be a Cl. And I will go this way with it, Cl. That takes care of that. Now, what is the rest of everything? The rest of everything is pretty much hydrogens. And the goal, right, is to get carbon to 4 bonds. So you want to put the appropriate amount of hydrogens in there to get everybody to 4. So for example, this guy here at the end on the far right has 1 line coming in, which means it has 1 bond, and it would need 3 hydrogens. That is a CH3, I think. That is really butchered there. When you clean that up there, try that again. Like up to the end of the screen. All right, let's try that again. All right. So this guy here at the end should have CH3. The guy next to it has 2 lines coming in. So to get him to 4, he needs 2 more. So that is 2. Same thing with this guy, 2 lines coming in, needs 2 more hydrogens to get there. This guy needs 2 hydrogens. I keep eating up my carbons. And this guy needs 2 hydrogens. And the guy here has actually 3 lines coming in, which means it needs just 1 hydrogen. This guy here has 3 lines coming in, so needs just 1 hydrogen. And that is all you wrote there. Yes. No, what I drew here was more be considered probably more like a condensed formula. Yeah. If you drew the structural formula, it would look just like that, but everything would be drawn out, all the hydrogens. If you did a little line structure there, that would be something like one. And off of our first one here, we have, and off of our second one, we have a methyl, sort of the line structure there. Now, again, if you kind of just drew out the hydrogen, that'd be more of the structural. Wow. Other questions on that? So again, always work backwards, start with just the carbons, put on all the groups in the proper locations, and then basically get everybody in terms of carbon to 4 bonds by putting the appropriate number of hydrogens. And you should be able to draw the correct structure at each time. So I'm going to go here, draw 3 bromo, 1 chlorobutane. Okay, let's take a look. So again, we're going to work backwards here in the name. So butane tells me I should lay out 4 carbons here. Takes care of that. 1 chloral means that's the first carbon that has a chlorine group, and I'm going to go left to right. So I'm going to again call this carbon number 1 here. So it doesn't really matter where you put the Cl. It could be on any side. I'll pop it up there on top. At carbon number 3, so since I called my guy on the left there 1, this guy here would be carbon number 3, would be a bromo group. That takes care of that. Now we are left with just hydrogens. Guy at the end needs 3 to get to 4 bonds. This guy needs 1. This guy needs 2, and this guy here needs 2 as well. Any questions on that one? Line structure would be 4, which looks like that. 1, 2, 3, 4. Again, off of the first carbon here, we have a chlorine. Off of the third carbon, which in my case would be here, has the bromine. Yeah. And again, I'm calling this carbon number 1 right there. Yeah. Any questions on either of those? All right, so let's try a couple more here, I think. So name each of these, see what you come up with. Okay, let's take a look. So first one, longest carbon chain, 1, 2, 3, 4, and 5. That looks like a winner there. So 5 would be pentane. There is just 1 group attached right there, which is a chloral group. And we need to figure out the numbering. So obviously just looking at it, you can probably see going right to left here, we'll give that guy the smaller number. So that's going to be 2 chloral pentane. Any questions on that one there? Looking at the next one, we got 1, 2, 3, 4, 5. That is the longest. You could also, by the way, if you wanted to get to 5, I think going this way, 1, 2, 3, 4, 5. So whichever way you want to go should be fine. But it does look again that 5 looks like a winner there in terms of how much. So we'll just take the straighter one there. So 5 again is going to be pentane as our main group. We have this group here and this group here. They both have nothing written at the end of the line, which means they are both methyl groups. So in line structure, if you see nothing written at the end of the line, it's assumed to be a carbon. And since that only has 1 line, it would also have 3 hydrogens, which would be a CH3 group. Again, not usually written, but it's basically a CH3 group out there. Going left to right here, I think it's going to be a winner in terms of our numbering, 1, 2, and 3. Obviously, if we go the other way, we're looking at like 3 and 4. So this is going to be 2, 3 dash, because there's 2 methyl groups, dimethyl, Remember, they don't have to be on the same carbon, but there's two of them in the whole entire compound. That is, again, why we need to give the number of both of their locations. And this would then be pentane. Again, here, the number separated by a comma, and then obviously our dash between our number and our letter. Any questions on that there, our naming or drawing? Okay. All right. So let's talk a little bit about some properties of alkanes. Alkanes are pretty much non-polar, as we talked about. They're pretty much carbons and hydrogens. Alkanes with only 1 to 4 carbons are typically gases. So things like methane, propane, butane, those are definitely gases. 5 to 8 have highly volatile liquids. Volatile means that they can go into the gas phase really quick. So things like pentane, hexane, heptane, and octane, like our gas, right? And then obviously things with a lot more carbons tend to have higher boiling points than things with less carbons. They have stronger dispersion forces kind of holding all those guys together. Really long carbons will end up being things that are waxy solids like petroleum jelly, Vaseline have like 25 carbons. They're very, very non-polar. Solubility, alkanes are non-polar. They're insoluble in water. They float. So usually, again, water on the bottom there and your organic guy up on top is usually how that sort of separates out. That's also because they are less dense than water. So they float to the surface, again, like an oil spill. The oil kind of stays on the surface as it's floating around. The type of reactions that alkanes undergo are ones that we talked about before. Mostly they do undergo combustion reactions. And these are the organic combustion reactions, usually produce heat and energy and flame. And the way you can recognize it is you got an organic guy plus O2 on the left, and it will make CO2 and water on the right. These are your two common combustion products that are made with an alkane or any organic, really. O2 on the left, and it's a pretty safe bet to write CO2 and water on the right-hand side. That is typically what they form. I think we had some practice balancing some of these guys when we were talking about equations and stuff like that. These are the guys sometimes you need to use a fraction to balance, as we talked about when we were doing that. So it usually gives off heat and energy. They're usually exothermic, releases energy in a combustion reaction. This is basically what happens when you light your Bunsen burner, right? You get a flame and all that good stuff. Just like if you use propane or butane to cook, right? You get a flame when you do that and you heat it up. But basically same reaction. This is butane, and we got O2, CO2, and water here. So again, a very much a combustion reaction that they undergo. Yes, sir. You should know what a combustion reaction is, yes. Now, here's just a couple of different ones for balancing. Again, you have to use the major reaction that alkanes actually undergo are what are referred to as substitution reactions. So in a substitution reaction, much like the name implies, something comes on and takes the place of somebody else. So they substitute for each other. And what happens usually with alkanes is simply it is a hydrogen that gets substituted. So if you take something like this alkane plus say Cl2, basically what's going to happen is any of these hydrogens you could pick, because they're all basically the same. One will come off, and one of these chlorines will come on in its place. And absolutely nothing changes except that one spot. So everything else is exactly the same. So what I had here is exactly the same as what I just drew. Still have the carbon and the hydrogen, which is this part of it, exactly the same. Only difference is I'm going to get rid of the hydrogen and pop on my chlorine. In addition, the hydrogen came off and we have an extra Cl, so we make HCl as the other thing that actually gets made, but the organic guy is here. This is what is referred to as the mono-substituted product, because you basically just took off one hydrogen. If you let this go under proper conditions, you'll take off all the hydrogens and replace them all. But usually you just ask to draw sort of the mono-substituted product. Also works the same like on a ring type situation, a cycloalkane. Although they're not typically drawn, there are hydrogens off of each of those carbons. So if you did the same type of deal here, one of those hydrogens comes off, one of the chlorines go on, and everything remains exactly the same. Nothing opens up, nothing goes crazy. You just put a Cl on there. Yeah. And again, you get your HCl in this case. So when you draw products for reactions of organic molecules, people like to do all kinds of weird things because they think it must be way more complicated than it is. It is not. There's really just one spot that changes. Everything else remains the same, which means that 99% of the time, you have almost 99% of the structure you need to draw right there. You just change the one thing that changes, and you'll end up with the right thing. Question on substitution reactions here. Question on alkanes. Okay, like I said, we're going to take an interlude here, and then we're going to now kick to chapter 12 and start talking about alcohols. The rest of this chapter we will do during discussion this week, since it's a little bit more relevant, I think, to the lab you're doing this week. So at least we can get a little bit in on alcohols here with what's left. So this will be chapter 12's opening part of the lecture. We're going to focus here on the last part here of this lecture on our good friend alcohols, which should be the first part of the notes, actually. So alcohols are another organic group. They have a functional group of the OH group is the functional group. That OH group is an important group because it is, like we talked about with bonding, a polar group, partially negative on the oxygen, partially positive on the hydrogen. It is a polar group that is attached. So that does give alcohols some important sort of functions, like they are sometimes soluble in water because they can hydrogen bond with water. Especially small alcohols are able to do that because of that OH group that is present. So in this chapter, obviously, we'll talk about alcohol styles, ethers, aldehydes, and ketones. But again, we'll just focus in here on alcohols. So the alcohols, like I said, have that functional group, which is the OH. So as soon as you see that group on anything, that is considered an alcohol. And as you can see here, not surprisingly, they are pretty much named very much off of those first 10 alkanes. This is a one carbon alcohol. One carbon is methane. Alcohols end in OL. So this is known as methanol instead of methane. So it's methanol. OL is the alcohol. This is a benzene ring, and it is different than cyclohexane because it actually has 3 double bonds in it. So that's not cyclohexane. This is what is known as benzene. And when you have a benzene that actually has an OH group attached to it, it is known as a phenol. So a phenol is basically a benzene ring that has the 3 double bonds in it and an OH group attached to it. A thiol we'll talk about is have an SH group, and ether has this carbon group. And again, we're going to talk about each of those guys as we go through this chapter, obviously. So let's talk a little bit about sort of alcohols. We could also do our normal condensed structure, and we could also do our line structure as well. You know, so if you had something like CH3, CH2OH, that is 2 carbons with an OH group. 2 carbons is ethane. This is known as ethanol, OL, at the end of it, which is the alcohol. And if you did like something like that, that would be your line structure for it. Again, 1 carbon, 2 carbons. And actually I have an extra carbon in there. Just do the OH at the end there would be good. All right. OH, there we go. And that would be obviously ethanol. So let's talk about how we name alcohols. Pretty much the same rules apply. You want to find the longest continuous carbon chain, but the longest continuous carbon chain needs to have the OH group in it. So the longest carbon chain that has the OH group in it will be your alcohol, and it will be your main part of the name. You will go to your alkanes, drop the ANE, put the OL at the end of it. Any other group that's attached, you will name like normal. You'll give the number and where it's located. The important part, though, is it is the OH group that takes the priority in terms of numbering. So we always want to give the OH group the lowest number. So whichever way gives the OH group the lowest number, you do need to include it and kind of name everybody. In addition, there is more than one place where you could put the OH group. And that happens right around 3 carbon. You need to give the location of where the OH group is at. So what I mean by that is something, there we go. I have this guy here. I got this guy here. The OH groups are in different locations. So if we go to name the top guy, we'd follow our normal rule here, which would be 1, 2, 3 is the longest carbon chain that has the OH group attached to it. So 3 carbons would be based off of propane. So this guy would be propanol. But we do need to give the location of where that OH group is, and it is at which carbon? Carbon number 1 is the smallest one. Doing that right? 1, 2, and 3. This is what propanol. The 1 is the location of where you find the OH group on the chain. If we look at the bottom guy, this is also 3 carbons that has the OH group there attached to it. So propanol. 1, 2. Actually, no matter which way you go, you have also known as isopropyl alcohol, also known as rubbing alcohol, because that is the same 3 names for the same thing here. Why is it called isopropyl alcohol? Because it actually has the isopropyl group we talked about earlier. That is CH3, CH, and CH3. So that's the isopropyl alcohol, sometimes called. Question on the naming. So about 3 or more carbons with an alcohol, you do need to give the number of where the group is attached. Do you have a question or not? Because that's 3 carbons, so it's based off of propane, right? 1, 2, and 3. So 3 carbons is propane, so it become propanol. Other questions? So that's the additional thing. Then obviously you would give the priority to the OH group, and any other group attached there would be numbered accordingly. So if we look at this guy here and we want to find our longest continuous carbon chain, just going straight across 1, 2, 3, 4, 5, 6, we could start up on top and come down 1, 2, 3, 4, 5, 6. So there's a few different ways you look like you could get them. So I'm just going to take the straightest 6 here. That's going to be the base of my name. So 6 carbons is hexane. Because it has the OH group, it's an alcohol, so it now becomes hexanol, right? It has one other group, which is a methyl group. And I do need to give the location of that OH group because it's more than 3 carbons. Where is that OH group? Which way should I number? Left to right or right to left? We should number, in this case, to give the OH the smaller number, right to left. So with the OH group, it takes the priority. So we do want to go right to left. Otherwise, obviously, if we went left to right, it would be a much larger number. So this is 2-hexanol, 2 for the location of where the OH group is at. Because I locked into numbering right to left, that means my methyl group now ends up at carbon number 5. So you can't change the numbering, you got to keep the numbering. And again, here we want to number whichever way gives the OH group the smaller number. So we end up with 5-methyl-2-hexanol. Again, hexanol, 6 carbons with an OH group. 2-hexanol means the OH group is at carbon number 2 in that chain. And at carbon number 5, you find a methyl group that's located there. Any questions on that name there? All right, so I want to take a second here and see what you come up with these guys. Give some names. See what you come up with. First one here. So it looks like it is 5 no matter which way you go. There's 2 ways. You could go straight and get 5. You could also start this way and go to the right and get 5. So since we have basically 5 as our max here, I'm going to take the straightest here. So 5 carbons is based off of pentane. It obviously has an OH group, so we're going to get our pentanol. Because again, it has more than 3 carbons, we need to actually give the location of that. And by looking at it, if we go right to left, that will give our OH group the smaller number. That means that this should be 2-pentanol for the location of where the OH group is located. Since I am numbering this way, that means my methyl group there is going to be at carbon number 4. So this should be 4-methyl-2-pentanol. Any questions on that name there? Yeah. Looking at the one to the left there, this again is our benzene ring that has the OH group. So that has a special name, and that is known as phenol. And because the OH group always gets the priority in terms of numbering, we would call this carbon number 1 where the OH group is located. And we would want to get this Br to the smallest number, which means we actually need to go counterclockwise here to go 2 and 3. Obviously, we went clockwise. That bromine would have ended up at carbon number 2, 3, 4, 5 versus carbon number 3 here. So because there's double bonds all through there, you could go counterclockwise or clockwise. It doesn't matter. And we could get the lower number there for our 3-bromol phenol. Any questions on either of those 2 names? Coming out over here, going backwards with the name. So pentanol is going to give us 5 carbons. So I'll go down here, 1, 2, 3, 4, and 5. 4-pentanol, my made up bad name here, means that carbon number 4 is going to be the OH group. I'm going to go left to right. So this for me would be carbon number 4, as that's carbon number 1. That means at carbon number 2, there would be a Cl. And then obviously everything else here, much like the other, will be hydrogen. So we need 3 hydrogens there. This guy has 3 bonds, so he needs 1 hydrogen. 2 bonds needs 2 hydrogens. 3 bonds needs 1. And the guy at the end there would need 3 in that case. Any questions on that one there? Lastly is cyclohexanol. So cyclohexanol is based off of cyclohexane, which is the ring. It is the ring with no double bonds. So difference, double bonds, no double bonds. So that is cyclohexanol. That's actually cyclohexane. Now I need to put an OH on it to make it cyclohexanol. Doesn't matter where I put the OH. The answer is it doesn't. You can put it anywhere you like along the ring, and that would technically be carbon number 1. And that's it, since there's nothing else attached, obviously. Question on drawing these alcohols. Yes. I'm sorry, say it one more time. Yeah. Okay. So when you're drawing, you can number it whichever way you like. So because I was drawing the 2-chloro-4-pentanol, I could have numbered left to right like I did, or I could have went right to left, would be perfectly fine. In the case of A, since the structure was already given to us, we have to number whichever way will give the OH group the smaller number. So we're kind of locked into, because it was actually drawn for us, it has to go right to left in that case. Yeah. Other questions? Yeah. Yeah, it actually should be that. That should be the right way. So sometimes what happens when you're asked to draw the structure from the name, when after you draw it, you look at it and go, I wouldn't name it that way. And it sometimes happens. Yeah, so you're right, because technically speaking, the OH group should have the smaller number. And it should, if you were given the structure on the bottom, what you said there is how you would name it. It would be 4-chloral-2-pentanol. But sometimes that happens when you're given the name and you draw it and it's not really correct in terms of the rules of naming it. But if you're given the name, you do want to just draw it, obviously, how it's written. Yeah. Other questions? And that happens a lot, actually, when you look at some names and stuff when you draw. Other questions on naming alcohols? So let's talk about a couple other things with alcohols here, which are important. First off, just like carbons, you can classify alcohols as primary, secondary, and tertiary alcohols. The deal is here, it works the same way, except we are looking at the carbon that has the OH group attached. So the carbon that has the OH group, how many carbons are attached to that guy is what we're looking at. Same rule, if it's 1 carbon attached to it, it's a primary. If it is 2 carbons attached, it's a secondary. And if it is 3 carbons, it's a tertiary. That means here, if we look at this one here, which I drew, which is ethanol, that is the carbon that has the OH group attached. How many carbons are attached to this guy? Just 1. Yeah, so there's just 1 attached to it. This is a primary alcohol. Again, the carbon that has the OH group attached, how many carbons are attached to it, that would give you your answer there. If we look at maybe some of the ones we did here, for example, this would be the carbon that has the OH group attached. How many carbons are attached to that one? Directly attached is 2. This would be a secondary alcohol. Yeah. So that is a secondary alcohol, 1 carbon there, 1 carbon there attached to that carbon that has the OH group. Let's see here. What would this one be? This, I think you said 2, and 2 would be right. This is technically the carbon that has the OH group. There's 1 carbon attached there, 1 carbon attached there. This would be a secondary. This guy here would be a secondary as well. Again, it has 1 carbon, 2 carbons attached. You draw maybe something here. This one would be primary, secondary, or tertiary. It would be, this is the carbon that has the OH group. It has 1, 2, and 3 carbons attached to it. It would be a tertiary alcohol. Question on how to identify those. I found the carbon that has the OH group attached to it. That would be the one in the box. And then what I am looking for is how many carbons are directly attached to the one in the box. And that would be 1 carbon there, 2 carbons, and 3 carbons, which would give you your tertiary. Other questions? So in this case, it is the carbon that needs to have the OH directly attached to it. And then what you're actually looking at is how many carbons are attached to that carbon. And that will get you your primary, secondary, tertiary. Question? Carefully. Ish. I'm gonna go with something like that. Give or take a letter or two here. I don't know, but something like that. I like to go that way. That way you just say tertiary, so. Other questions? All right. So these are really important for some of the reactions that alcohols go through. So for the last couple of minutes here, let's talk about some of those, which again might be helpful for your lab. Alcohols undergo one type of reaction, which is oxidation and reduction reactions. And we talked about oxidation reduction reactions, I think, when we talked about types of reactions. There are a few definitions of oxidation, but a couple of definitions are they lose electrons, it gains oxygen as it goes from reactants to products, and it loses hydrogen as it goes from reactants to products. Reduction is the opposite. It will gain electrons. It will lose oxygen as it goes from reactants to products, and it will gain hydrogen as it goes from reactants to products. So in organic chemistry, we really don't deal with electrons a lot. We deal with really oxygen, hydrogen sort of being gained and lost when we talk about oxidation and reduction. And it's important in alcohol reactions. And let's talk about sort of what happens in these couple of types of reactions here. I'll just draw some here. So if we take an alcohol like this guy here, I'll just draw it out. Actually, that's fine. It will go through an oxidation, which is sometimes represented by a little bracket there with an O in it. Now, first off, what type of alcohol is this one again? It's a primary alcohol. Again, looking at this guy, it has 1 carbon directly attached to it. But the definition of oxidation that occurs with primary alcohols is we will lose H2. Where does the H2 come off of? Well, it will always come off of these 2 locations. It will come off of the carbon and the hydrogen. So those 2 is where the hydrogens come off, and you get H2 that pops off, obviously. Now, what happens is everything stays exactly the same on this guy. I'm just going to draw exactly what I got over there. I'm going to draw the H, the C, the H, and the H, and the C, and the H, and the O. I'm obviously not drawing the 2 H's I have in boxes, right? I just took those out. Now, we talked about what happens when you lose 2 hydrogens. That's usually associated with making what? In organic chemistry, every time you make a bond, you lose 2 hydrogens. So that's exactly what happens here. Who would be short here in terms of bonds? It is between the carbon and the oxygen is where the double bond comes into play. So you basically lay up a double bond. That's the only difference. This makes what is known as an aldehyde. And that is the functional group of an aldehyde is actually this guy right here. So if you take a primary, you put it through an oxidation reaction, you always take a hydrogen off the carbon that's attached to the OH, and you take the hydrogen off the OH. And you just simply make a double bond between the carbon and the oxygen. Everything else stays exactly the same. Question on that one there. If we had an alcohol like this, perhaps. and we go through an oxidation reaction. What type of alcohol is this one? Secondary is correct. This is a secondary alcohol. Again, this is the carbon that has the OH group attached directly to one carbon there and two carbons there, right? The exact same thing happens. You lose H2, and the H2 is lost in the exact same spot, which means I'm going to take an H off of the O, and I'm going to take an H off of the carbon. Everything else stays exactly the same. So I'm not even going to think about it. I'm frankly going to copy what's there. Obviously not drawing the guys that I boxed out, which are the hydrogens. So I end up with something that looks like this. And now what should I do between the carbon and the oxygen? Yes. And this makes what is known as a ketone. The group of a ketone is 3 carbons in a row with a double bonded oxygen in the middle. And that is this guy right here. That is 1 carbon, 2 carbons, 3 carbons with the double bond in the middle. And that makes a ketone. So if you oxidize a primary alcohol, you get rid of the 2 oxygens, you make an aldehyde, double bonding between carbon and oxygen. If you have a secondary alcohol, you dump out 2 hydrogen. You're doing an oxidation reaction, double bond between the carbon and the oxygen, you get a ketone. So that leaves us our tertiary alcohol. And let's talk about what happens with that guy. Actually, let's not talk about that. Let's see here. Let's go here. I think will work. So if we took a tertiary, everything here. Tertiary alcohol. Again, carbon right here, attached directly to 3 other carbons. I want to do a little oxidation action. So I'm going to take the hydrogen off of the oxygen. And the hydrogen should then come off of the carbon, correct? That is attached to the OH group. Is there a hydrogen there? There is not. There is no hydrogen, which means no reaction, because it is missing the second hydrogen that is necessary. So a tertiary alcohol will not go through an oxidation reaction because it does not have a second hydrogen needed on this carbon, not the other carbons, but that carbon right there. Because it's missing the hydrogen, it will not go through oxidation. So those are the 3 sort of oxidation reactions that alcohols undergo. A primary will make an aldehyde. It could do that, hydrogen off of the oxygen, hydrogen off the carbon, double bond the carbon, oxygen, draw everything else exactly the same. The secondary alcohol will oxidize to a ketone, same thing, hydrogen off of the oxygen, hydrogen off of the carbon, double bond the carbon, oxygen, don't change anything else. Tertiary alcohol cannot go through oxidation because it's missing that second hydrogen. Question on any of those? By the way, the reduction reaction is the opposite. Reduction reaction. I didn't reduce it, add the hydrogen back in, you get your alcohol back. You start with a ketone, add the hydrogen back in, you get your secondary alcohol back. Remember, oxidation reductions are always tied together, so they're basically kind of opposites of each other in these type of reactions. Any questions on that? I hope that will help you for your lab this week. Yes. This page? Yep. Other questions? Okay, we will obviously lay it up there right